In this video, we are going to have a look at one of the most commonly used protein language models during the last couple of years, the ESM-1b transformer network, where ESM stands for evolutionary scale modeling. We will shortly look at its model architecture, the training process, and for what the trained model can be used. In the next videos, we will also have a look at alternative protein language models, including the successors of the ESM-1b model. The ESM-1b transformer network is an open source protein language model that was published by Rives et al., who were part of the Facebook or Meta AI research team in the journal PNAS in 2021. The architecture of the model is a transformer network encoder, which is very similar to what you have seen in the previous videos. And the model was trained for the training task that you have also seen before, the prediction of amino acids that were masked in the input sequence. We will have a closer look at the exact architecture and training of this model on the following slides. The architecture of the ESM-1b model is, with a few small exceptions, identical to the encoder that we've seen in the previous video. The representation dimension of the encoder is equal to 1280, and the number of attention heads in each multi-head attention block was set to 20. And we already know that in order to get the representation dimension of each attention head, we need to divide the total dimension d by the number of attention heads, 20, which is equal to 64. So the dimension of each attention head is actually quite small. The maximum sequence length is set to 1024. Since most protein sequences have a shorter sequence length, this is not a problem in most cases. However, the model was only trained to learn positional embeddings for the first 1024 positions. So if we want to apply the model to longer sequences after training, we couldn't apply the model to the full sequence, because we simply have no way of encoding positions over 1024. What you would typically do is you would simply use the first 1024 amino acids in the sequence and omit the rest of the sequence. We will later see that the ESM2 model is capable of also handling longer sequences. The hidden dimension of the feed-forward neural network was set to 4 times the size of the dimension d, which is equal to 5120. There is a total of 33 such encoder layers, which results in 652 million learnable parameters. And as I said, the architecture is mostly identical to the encoder that we've seen before, with a few exceptions. One such exception is that they applied the layer normalization before the attention block and before the feed-forward block, instead of applying it afterwards, because they found this slightly improves model performance. But this didn't affect overall performance very much. Another small difference is that in the feed-forward block they used a GELO activation function instead of a ReLU activation function. As you know, the ReLU function is 0 for negative values and leaves positive values unchanged. The GELO function is very similar, but as you can see, it also returns small negative values for small negative input values, which means this function provides a smoother output compared to ReLU for values that are close to 0. This can help optimization by avoiding sudden gradient jumps, and the smooth behavior better preserves information through deep layers. Let's have a look at how the ESM-1b model handles the positional encoding and the token embeddings. In contrast to what we have considered so far, the ESM-1b model uses learned embeddings for all possible amino acids or tokens. These embeddings have dimension of 1280, which is also the dimension of all token representations in the model. This is the variable that we named d on the previous slides. For the positional encodings, the authors tested both learned representations and also the predefined sinusoidal positional encodings, but they found that learned positional encodings led to better results. As you know, the positional encodings need to have the same dimension as the token dimension, so they also have dimension 1280. But how can we actually learn token and positional embeddings? I'm going to show an example for the token embeddings, but the principle is the same for the position embeddings. What we learn during training is basically the entries of a matrix where each column in the embedding is the embedding of a specific amino acid or token. In this case, we would have one column or one vector for each token that can be the input of the model. Additionally to the 20 tokens for the 20 amino acids, we could have one padding token that we can use to ensure all sequences of a batch have the same input size, one token that represents a masked amino acid, and one token for unknown amino acids within a sequence. Later, when training the model for a supervised task, we will see that we will also have a so-called classification token for capturing information about the whole protein sequence. But now let's assume we have 23 different tokens that we want to encode. When applying the model, we can access each token representation quite easily by encoding the type of token in a binary vector. Let's say we have the second amino acid at a certain position, so we generate a vector with all zeros and a single one at the second position. If we multiply our embedding matrix with this vector, this results in a single vector that has in its column the entries of the second column of the representation matrix. So this is our embedding for this token. And since all entries of the matrix can be adjusted or learned during training, we have learnable embeddings. This works very similar for the positional encodings. Instead of having 23 columns, the number of columns depends on the maximum sequence length that is allowed. In the case of the ESM-1b model, the maximum sequence length was set to 1024. So we would have a 1024 by 1280 dimensional matrix that stores the learnable positional embeddings. And we would also encode the different positions of an input sequence in a binary one-hot encoded vector to access the different positional embeddings. This model was trained for the masked token prediction task. And similar to what we have seen before, they have selected randomly 15% of the input tokens, which they wanted to predict with the model. However, instead of replacing all of these tokens with the masked token, they only replaced 80% of these selected 15% with the masked token. 10% of the selected tokens were replaced with a random amino acid, and the remaining 10% were left unchanged. Even if not all of these selected tokens were masked, they still trained the model to predict the true amino acid type for all of those selected tokens. This approach was compared to the approach where all of the selected tokens were masked, and was found that using this approach led to slightly better results, but the difference was not very big. During this training task, they used tied input-output embeddings. This means that the same learnable token embedding matrix that we have seen on the previous slide is used both to turn the input amino acid tokens into vectors at the start of the model and to turn the final hidden token embeddings back into predictions over amino acids at the end. Technically, when the model sees an amino acid, it looks up a vector from the embedding matrix W to represent it as a d-dimensional vector. After processing the sequence through all the layers, the model then uses the same matrix again, but this time in reverse. It compares its final hidden and updated d-dimensional token embedding against all the entries in the embedding matrix to guess which amino acid fits best. By comparing, we mean computing the scalar product between the updated token embedding H and each learnable token embedding from the matrix W. We know that more similar vectors will lead to larger scalar values when computing these scalar products. And the main advantages of using tied embeddings are that we have fewer parameters because the model does not need to store two separate matrices, which saves memory and reduces the size of the model. And we have better generalization because sharing the embeddings helps the model to learn a closer relationship between how amino acids are read and how they are predicted, which can slightly improve model performance. As a training dataset, they used the UniRef50 dataset, and this dataset is based on the UniProt database, which stores a total of 250 million protein sequences. The UniRef50 dataset is a group dataset, which groups sequences that have sequence identities over 50%. And then from each of those groups, only one representative is selected, which results in a dataset of approximately 30 million diverse protein sequences. The training process for the ESM-1b model was computationally quite intensive. They trained it for around 20 days using 64 NVIDIA V100 GPUs running in parallel. Each training epoch, meaning one full pass of the entire dataset with 30 million sequences took about 8.5 hours. In total, they trained the model for 56 epochs. And they used the ESM optimizer for training, which is a popular optimization algorithm that works well for large neural networks. The learning rate was set to 10 to the power of -4, and the beta parameters were set to 0.9 and 0.999, which are standard settings for the ESM optimizer. And to make training faster and more efficient, they used dynamic batches. All sequences were either truncated, so there were no longer than 1024 tokens. Then sequences were grouped into batches based on their length. Shorter sequences were grouped together so that more of them could fit into one batch, and longer sequences were grouped together in smaller batches. Each batch contained sequences of different length, but all sequences inside a batch were padded to match the length of the longest one inside of this batch. Importantly, they adjusted the number of sequences per batch so that the total number of tokens stayed roughly the same for every batch. This way, they could keep the computational load balanced and make sure that they best use their available GPUs. Finally, we will look at how the ESM-1b model uses dropout. Dropout is a popular technique used in neural networks where during training some neurons are randomly turned off to prevent the model from overfitting. The benefit of dropout is that it helps prevent overfitting by forcing the network to not rely too heavily on any one neuron or node, encouraging it to learn more robust general patterns that work well on new unseen data. If we compare ESM-1b to a standard transformer, we can see some important differences in how dropout is applied. In a standard transformer, dropout is usually used both inside the attention layer and the feed-forward layers. But in ESM-1b, they actually decided to not apply dropout in either the attention or the feed-forward layers. So those parts of the model are trained without randomly dropping activations inside those layers. Instead, ESM-1b uses a different strategy. They apply dropout at the word or token level, but specifically only for the masked tokens during the masked language modeling prediction task. In standard transformers, a type of dropout is usually applied after combining the word embeddings and position embeddings, but not directly at the level of individual words or tokens. In contrast, ESM-1b applies dropout directly to the masked tokens themselves, which means instead of learning a token representation for the masked token, as would be usually the way to do it, they simply set the token embedding values for the masked tokens to all 0 values. So let's see if the model actually learned representations that store useful and meaningful information. On the one hand, the authors tested if the model learned structural information from seeing only the linear amino acid sequence and having no information about the folded 3D structure of the protein. On this slide, you see a contact map for a protein that shows which amino acids are close to each other in the folded 3D structure of the protein. On the X and Y axes, we have the amino acids numbered as they appear in the protein amino acid sequence. So this is a protein with a little bit over 300 amino acids in its sequence, and the black dots indicates if 2 amino acids are close to each other. You see this black diagonal line because obviously each amino acid is close to itself and to amino acids next to each other. But you can also see other black points where, for example, amino acid 50 is close to amino acid 250 in the 3D structure of the protein. We can now use the learned amino acid representations of the ESM-1b model to predict for 2 amino acids if they are close to each other. In this case, we would not calculate the element-wise mean over all amino acid representations to get a single whole protein representation, but we would use the amino acid representations themselves. If we can successfully use the amino acid representations for this task, this would show that they also store structural information. And this can be formulated as a binary prediction problem where we want to predict for all pairs of amino acid representations I and J, where I and J are the positions in the protein sequence, if those 2 amino acids are closer than a certain threshold to each other or not. In the ESM-1b paper, this was done by first calculating a linear transformation of Hi and Hj by multiplying these matrices by matrices P and Q. Then we can calculate the scalar product of both new vectors, which results in a single value. Then we can add a constant value b, and we apply the sigmoid function, which results in a value between 0 and 1, where we interpret all values above 0.5 as positive, which means being close to each other, and we interpret all other values as negative predictions. The parameters of the matrices P and Q and the value B are learned during the training process for the prediction task. And it is indeed possible to predict the entries of such context maps reasonably well using ESM-1b amino acid representations, showing that they store structural information. On the previous slide, we have seen that the ESM-1b model generates representations that store structural information. But how about the function? Can we use the learned representations to predict the functions of proteins? Since we already know that protein structure determines the function of a protein, it is likely that we can do this. And indeed, ESM-1b vectors have been used successfully for a wide variety of different protein prediction tasks. Here we are considering the whole protein ESM-1b vector again, which is the element-wise mean of all amino acid representations. For example, these vectors have been used to predict the functions of enzymes. There are hundreds of different classes of enzymes that all catalyze different chemical reactions, and we can use the ESM-1b vectors to predict to which class an enzyme belongs. Or we can use these vectors to predict which substrates transport proteins can transport across a membrane. Or we can predict protein-protein interactions, or if a certain drug is inhibiting the function of a protein. This shows that the ESM-1b vectors indeed store a lot of useful information regarding protein function. To make these protein function predictions, we could calculate the ESM-1b vectors that we call vector E here for all proteins for which we want to make a prediction. This can be the vectors that we obtain after pre-training without further fine-tuning. Then we would train a separate machine learning model, for example, a linear regression or logistic regression model, or fully connected neural network, or gradient boosting model to predict the property or function of interest. In my experience, gradient boosting models typically result in best model performance among these models when applied to ESM-1b vectors for protein function or protein property prediction. Alternatively, if we have enough computational resources and enough training data for our prediction task of interest, we will see that we can also fine-tune the pre-trained ESM-1b model directly for our prediction task of interest. We will see how we can do this in a future video. If you want to use the trained model and get either the amino acid representations or the average mean representation of the ESM-1b model, you can use the Python package FAIR-ESM. You can install this package using pip install FAIR-ESM. And here I use an older version 0.4 of this package. We then need to load the trained ESM-1b model. If you do this for the first time, the model will be downloaded from the internet, which can take a few minutes. We also load the batch converter that converts an amino acid sequence into the input tokens for the model. So let's look at an example for calculating ESM-1b vectors for protein amino acid sequence. Here I used the protein amino acid sequence with 371 amino acids as an input. We used the batch converter to get the input tokens for this protein. Then we compute all ESM-1b representations for this protein. Since we want to get the amino acid representations from the last layer, you can see that we access the representation from the 33rd layer. Now we want to take the element-wise mean of all amino acid representations. The first token is a special token, so we don't use that, but we start at position 1 and go up to position 372. And we take the mean across those representations. And you can see that this results in a vector of dimension 1280. If you want to have the representations for each amino acid from the last layer, you would simply not calculate the mean here.